Shushan Kumar Rai, and I am excited to present my project profile for Emergee Embedded Internship. My project is about the real-time electric vehicle and ADAS dashboard. So, in the modern automotive industry, the transition to electric vehicle and the integration of advanced driver assistance system, that is ADAS, are happening at a incredible pace. So my project focus on bridging these two domains by designing and simulating a real-time telemetry processor and visual dashboard. So for this project I have used a microcontroller STM32 F103C86 with blue pin, which is simulated via Pixin Lab, and also it is paired with ultrasonic sensors, and my data is being shown through a Python dashboard. Now, what is the real motivation behind this project? The primary problem we face with modern EVs is data density. An EV vehicle generates massive streams of high frequency data from battery, that is state of charge, and motor temperature to high torque. At the same time, safety sensors are capturing multiple data. So, without a centralized high-speed processing unit, safety hazards like blind spot intrusion or forward collision can easily go completely undetected. So, our solution is telemetry, real-time speed SOC, and temperature tracking. ADAS core, forward collision warnings, blind spot checks, and proximity calculation. Priority alerts, multi-tiered hardware alarm, escalation, drive control, real-time drive mode, that is eco, normal, and sport. Let us look closely at how data flows through our system architecture. We have sensor inputs, that is accelerator, pedal, brake pedal, motor temperature, which are sampled at high frequency using STM32 on-board ADC. Now, timing input. So we have three SCSR0 for ultrasonic sensors representing the front, left, and right zones. These inputs are fed directly into processing pipelines of our microprocessor. The EV dynamics engine runs calculation for speed, torque, state of charge, regenerative braking. Currently, the ADAS engine computes obstacle distance, engine computes blind spot threads, and time to collision. Both engines feed their results into a fault and alarm state machine. If anomalies occur, the system evaluates the alarm level and structures the data into highly packed telemetry frames. These frames are serialized and pushed over a UART communication bus at a rate of 11,200 per second to host Python matplotlib dashboard. Now this complex system was made through 9 phases. First, dev environment, that is phase 1, stabilizing our environment, STM32 Cube IDE, fixing lab. Phase 2 and 3 involves configuring GPOs, status LEDs, and ADC samplers. In phase 4, we design mathematical EV dynamics model calculating speed, torque, SOC, range, and region. In phase 5, we configure for front, left, and right distances, and in phase 6, brought everything together under a central fault and priority alarm state machine. In phase 7, designing robust structure transmission frames for continuous feeds, and phase 8, bidirectional communication for light system property injection, and at last, the phase 9. We build a real-time UI with the help of MATLAB, Matplotlib, and graphic visualizer. Now, ultrasonic ADAS engine. Forward collision warning, time to collision is calculated, blind spot is detected, and it also gives parking assist system. So it also detects fault and gives alarm, that is over temperature, low battery, collision, sensor failure, etc. If only one alarm is buzzing, sorry, LED is showing or only one alarm is showing, then it is a normal operation, no active hazards or fault state. For alarm advisory 1, blind spot target presence or over speed indicator. For alarm warning 2, front collision warning reached. For alarm critical, immediate danger. In UART phase, we designed highly efficient lightweight protocol to pipe data to dashboard, which show vehicle speed, state of charge, motor torque, motor temperature, fault, time to collision. Now in Python dashboard, we get to see a speedometer, battery and range meter, speed history, ADAS bird view, metric detail panel, etc. So thank you. Look at my project. This is my STL32 cube ID. It's taking time to open. So this is my whole project. UVDAS in final project. We have core, we have ANC, SRC files, INC, ls.h, common.h, UV control.h, fault.h, link.h, SRC-cv control.c. So now we will clean this project. Here we are getting 0 error, 0 warning. It's time to build the project. So we will build this project. We are getting 0 error. Now we are opening Pixim lab. This is my Pixim lab. So we will load file. We have loaded. Also we can see that my configuration, how I have connected or configured all my pins. You can see that from here. So this is my 4 potentiometer. First one represent accelerator pattern, second brake pattern, third one SOC, and fourth one motor temperature. And this indicate front and this is ultrasonic sensor which indicate front distance, this left, this right, and there are 4 LEDs, red, blue, green, yellow, and this is virtual turn which is giving output, virtual output. As I am sliding this, making collision warning, and you can see that data is shown in data is shown here. I can fill my data. Everything is displayed here. Now this is my Python dashboard. It is showing the speed. Now I will be increasing the speed. Increasing slowly as I increasing is my, here you can see that I am getting front collision collision warning, alarm advisory. Also now also I will finish the script. So this is my final project. Thank you.